This is our next video in the series about the New York State Regents Physics course. This topic is current electricity. This is section 8.6, and in this section I will be discussing resistivity and what I like to call the wire equation. Resistance equals resistivity times length divided by cross-sectional area. Resistivity is the ability of a material to impede the flow of charge. In this case, since we're talking about electricity, we'll say that the material is impeding the flow of electrons. Now, resistivities are given on a chart. You can download the chart from this website, nysedregents.org, click on reference tables, and then scroll down until you see the physics charts. And I would recommend downloading all 6 pages of the physics reference tables because they're useful for the entire course. All right, so again, download this chart, which I've copied here from that website. Now, notice that the resistivities were calculated, or measured, I should say, at a specific temperature. So if you change the temperature, the resistivity is going to change. Generally speaking, when the temperature increases, the resistivity of materials tend to increase. Now, take a look at the unit for resistivity. This is ohm times meter. Now, be careful. It's not ohms per meter. All right, don't say ohms per meter because that's not what this is. This is ohms times meter. All right, if you accidentally say ohms per meter, that's going to be wrong. Now, take a look. These are metals, all right, aluminum, copper, gold, silver, tungsten. Nichrome, all right, is an alloy or a homogeneous mixture, a solution of two metals that have been melted down together. Sometimes nichrome has a little bit of iron or some other metal in it, but generally speaking, it is an alloy of nickel and chromium, all right? And notice that the nichrome has the highest resistivity on this chart. All the exponents are the same, so 150 would be 150 times 10 to the negative 8 would be the highest resistivity on this chart. All right, the lowest resistivity on this chart would be silver, 1.59 times 10 to the negative 8. Now, I just want to put this into proper scientific notation so you get an idea of the scale here of how much greater nichrome is than all the others on the list. All right, 150 times 10 to the negative 8, putting this in proper scientific notation, if you move the decimal 2 places smaller here, this would have to become 2 places greater, all right, to negative 6. So if you were to put nichrome in proper scientific notation, 1.50 would be times 10 to the negative 6. That makes nichrome, all right, with a 100 times greater resistivity than everybody else on this list. All right, because you've got 2 places here, all right, when you put them both, when you put everybody into correct scientific notation. Correct scientific notation meaning that there is only one number in front of the decimal point, all right? So that's just a minor, all right? And again, guys, I want you to understand that this number, 150 times 10 to the negative 8, is exactly the same as this number. Right? These are the same amount. Right? They're just written, this is in correct scientific notation. This one is written to correspond with the chart. All right. So, what does resistivity on this chart mean? All right. First of all, the word impede. Impede means to resist, to stop, to decrease, all right, to get in the way. All right. So, resistivity means the ability of material to kind of slow down the flow of electrons, let's say. All right, so for example, if you have metal, all right, a piece of wire, all right, here's a piece of wire. The piece, all of these metals have a very, very low resistivity, all right, 10 to the negative 8. relatively speaking, is going to be a low number, and it's going to be a low resistivity. So the metal, right, the metal is a good conductor, right? The metal is a good conductor because it does not resist or impede the flow of electrons. The resistivity is very low, so it allows the electrons to go through, all right? It allows the electrons to go through very easily. Here they are. Here's my electrons. They're flying through the metal because the metal has a very low resistivity. It does not resist the flow of electrons. It allows them to flow through easily. All right, so metals are going to be good conductors. All right, something like a piece of rubber, all right, we'll have a rubber rope here, or rubber wire, which doesn't even make any sense, but rubber or a non-metal, right, would be a poor conductor, all right, or a good insulator, because it does not, right, it's taken a long time. It does not allow the electrons to go through, all right? They're kind of getting stopped short, right? They don't want to go at all, all right? So the rubber is a poor conductor, right? The metal allows the electrons to go through. The rubber does not want to let the electrons go through. So that makes rubber a poor conductor. All right, so on this chart, the best conductor would be the one with the lowest resistivity. So that would be silver. All right, on this chart, all right, silver would be the best conductor. All right, and you can imagine what the second best conductor, all right, the third best conductor, the poorest conductor on this chart, although it's still a good conductor, relative to things like plastic and wood and rubber, which are not on the chart, the poorest conductor on this chart would be nichrome because it has the greatest resistivity. So, what's the difference between resistivity and resistance? Well, resistivity is the ability of a material, such as copper or plastic, to impede the flow of charge. Resistance is the ability of a device or an object to impede the flow of charge. So what we're saying is that if you go to Michigan and go to the mine and take out a chunk of copper from the mine, that's a terrible drawing of a chunk of copper, but you get the idea. So you've got this piece of copper that you took out of a mine in Michigan. All right, this is a material. All right, this is copper. This is pure copper. Now, if you build a piece of wire, if you construct wire out of that copper, all right, so let's make a copper wire, all right, and this is a blown up diagram of a piece of copper wire. The copper wire would be much, much thinner, all right. On the end of the copper wire, there's going to be a circle. If you chop it off, if you chop off a piece of wire, you're going to see a little circle at the end of the wire, all right? And a certain amount of this wire, right, a certain length of wire would have a certain resistance. Now, the way you calculate the resistance of a device or an object is to look at, all right, calculate the resistance of a device or an object. You look at what the wire is made out of. The symbol for resistivity is the Greek letter rho, all right? And you multiply that by the length of the piece of wire, and you divide by the cross-sectional area of the wire. In other words, the end of the wire shows that the area, the cross-sectional area of the wire, looks like a little circle. So down here you would put the area of that little circle. All right? But basically what this equation is saying is that ultimately the resistance of the device or the object depends upon what the object is made out of, which would give you the resistivity, the length of the object, and the cross-sectional area of the object. Now this equation works for a piece of wire, all right, wire. This equation also works for what we call a conductor. All right, let's draw a conductor next. All right, a conductor would be like a metal rod. Right, so here's a straight metal rod, right, a rod. Okay, let's say the rod is made out of copper or aluminum or silver. Right, so the rod, just like, although it's much larger than a piece of wire, right, in general, the rod would also have a length and a cross-sectional area, and it would be made out of some kind of metal for which you would get the resistivity, rho. All right, so the difference between resistivity and resistance, resistivity is a measure of the ability of the material, the pure material, right? Resistance is a measure of the ability of a device or an object that you have constructed out of a particular material to impede the flow of charge. And remember, this rod is generally called a conductor. And you'll see problems, questions, where they're asking about a piece of wire, and you'll see problems or questions where they're asking about a conductor. In either case, you will probably go straight to this equation, which I like to affectionately call the wire equation. And this equation is for pieces of wire or conductive rods. So let's take a good look at the wire equation. The wire equation says that the resistance of a piece of wire or a long cylindrical rod, a conductor, right, probably made out of metal, the resistance of that wire or that conductor is going to be equal to rho. Right, now that's the Greek letter rho. It looks like a little P. I like to put a little hook in the front to kind of distinguish it from a letter P. All right. So the Greek letter rho times the length of the wire or the conductor and divided by the cross-sectional area of the wire or the conductor. So in this equation, all right, we have resistance, right, which the symbol is R and the unit is ohm. We have resistivity, all right, resistivity, which the symbol is rho. Again, rho, this is the Greek letter rho. It's not a lowercase p. All right, and the unit for resistivity is ohm times meter. Right, don't say ohms per meter, say ohm meter. Right, you could just say it's an ohm meter. All right, length, nice and simple. The symbol is L, the unit would be meter. All right, and cross-sectional area. When you look at a piece of wire, right, here's a piece of wire. The end is a little circle. The area of that circle is what we're talking about here. If it's a rod, all right, the rod has a circle at the end, just the same. Rod, R-O-D. This is a wire. This is a rod, and often the rod is called a conductor. Generally speaking, both of these, when we're doing physics calculations, both of these would be made out of some highly conductive material with a very low resistivity. Generally speaking, a metal or an alloy. Right, aluminum, copper, silver, gold, tungsten, nichrome, etc. All right, the length now here, cross-sectional area, all right, capital A, and the unit for area, you know, it's meters squared. Okay, so that's the wire equation. Just a quick word about how to calculate the cross-sectional area, that would be a circle, of a piece of wire or a conductor, which would probably be a metal rod. Now again, if you have a piece of wire and you cut the end off, the end is going to look like a little circle. All right, this is a piece of wire. All right, if you have a metal rod, all right, and you cut it, which would be a lot more difficult, all right, you're going to see a little circle on the end just the same. So what you're trying to calculate, all right, we're going to call this a conductor. What you're trying to calculate to get the letter A, all right, if it's not immediately given to you in the problem, is you're trying to calculate the area of this little circle on the end of the wire, or this area of the circle on the end of the rod. All right, so we need to very simply calculate the area of a circle. So let's take a piece of wire and make it really, really big. All right, and let's take the radius of that wire, R. All right, and let's say that the radius of the wire, all right, let's say that R equals 0.150, and let's put it in millimeters so we can practice converting millimeters to meters. All right, so if you need to calculate the area of this circle, you know that the equation for the area of a circle is pi r squared. All right, but the first thing we're going to have to do, because in the physics class we tend to work in meters, not millimeters, the first thing we have to do is use the factor label method or dimensional analysis to convert 0.15 millimeters to meters. All right, so 0.150 millimeters. All right, we're going to convert that to meters. All right, you want the millimeters to go away, so you put millimeters at the bottom. I like to get all the units straightened out first before I put in any numbers. Put millimeters at the bottom because you want the millimeters to go away. Remember, this is really over 1. Then on top here, you want meters. Now, in this parentheses, the two things, top and bottom, the numerator and the denominator, must equal each other. So 1 meter equals 1,000 millimeters. All right, so now what you do is 0.15, all right, 0.15 divided by 1,000, all right, and we're getting 1.5 times 10 to the negative 4, all right, equals 1.50 times 10 to the negative 4 meters. All right, so that's the radius of the end of the wire in meters, all right? So now, let's hold on to that number, all right? And let's start plugging in to get the area of the little circle at the end of the wire. All right, so let me move this over a little bit, all right, so it can be nice and neat. So the area is going to be pi r squared, all right? For pi, let's use 3.141, that's fine. It would be 3.14159. I never memorized 100 places of pi. I'm sure some of you have, and congratulations, because I don't think I could do it. All right, 1.50 times 10 to the negative 4 meters. This whole thing gets squared. Okay, so let's do this. All right, 1.5 times 10 to the negative 4, raise that to the second power, all right, and then multiply that by 3.1415, all right. So the area, the cross-sectional area, is going to be 7.07 times 10 to the negative 8, and that's meters squared. All right, so this is the cross-sectional area, the area of the little circle at the end of a piece of wire. And you would do the same process if you were calculating the cross-sectional area of a conducting rod. Now, let's use our rules to figure out how different aspects, different parameters, different pairs of parameters are related according to this equation. Now we see that resistance and length are both on top, on opposite sides of the equal sign. Do you remember what kind of relationship that would be? Yes, that would be a direct relationship. Resistance and length would be directly related. In other words, if you take a longer piece of the same copper wire with the same area, you would have more resistance. Now, what about resistance and area? How are resistance and area related? All right, let's just fix that really quick. All right. How are resistance and area related? I like to just circle like that. All right. Resistance and area, because they're on opposite sides of the equal sign. One is on the top in the numerator, and one is on the bottom in the denominator. What kind of relationship is that? That is an inverse relationship. They are inversely related. Okay? Now, for length and area, keep this in mind. Keep in mind that changing the length of a piece of copper wire is not going to change its area. All right, what you would have to do for that, all right, R equals rho L over A. All right, if you wanted to say how are length and area related, you would have to say, well, if I want to have, now for example, let's say that it's two pieces of copper wire, so that the resistivity is not going to change. It's going to be copper and copper. But you want the resistance of both pieces to be the same, right? But they are going to be different lengths. You are going to change the length. So the R has to stay the same. The P has to stay the same. And you want to know if you change the length, let's say you use a longer piece of wire, all right? What would the area of that second piece of wire have to be in order that the resistance and the resistivity do not change? Well, resistivity is not going to change anyway because it's a constant for copper. But the resistance is something that could change. So, if you use a longer piece of copper wire, all right, would the area have to be bigger or smaller to have the same resistance? Well, since they are on the same side of the equal sign, and one is on the top, all right, and one is on the bottom, this is a direct relationship. The length and the area would be directly related. That means if you're going to use a longer piece of wire, that piece of wire would have to have a greater area, all right, increase, direct relationship. That piece of wire would have to have a greater cross-sectional area to have the same resistance as the shorter piece. So our second piece of wire would look something like this. It would be longer, right? And the cross-sectional area would have to be greater. I'll do it like that. What a mess. But you get the general idea. In other words, this longer piece, where the length is increased, would have to have a greater cross-sectional area in order to have the same resistance as this piece. So length and area are, again, directly related. Let's try a real problem. I have a piece of wire here, and the resistance of this wire is 20 ohms. What's going to happen to the resistance if I double the length? So what would the resistance of this piece of wire be? Well, you notice since resistance and length are on opposite sides of the equal sign and both on top, this is a direct relationship. So if you double the length of the wire, the resistance of the wire is going to double. The resistance of this new piece of wire will be 40 ohms. Now, a shortcut to figuring this out would be to take the equation and just put a 2 over the length because you just doubled the length. Well, 2, nothing on the bottom changed, so we'll just put a 1 down there, all right? 2 times. The new resistance will be double also. So if I double the length, the resistance is doubled. If the resistance of the original piece of wire is 20 ohms, if I take a piece of wire where everything else is the same, it's still made out of copper, and the cross-sectional area is the same, the only thing that changed is that the length was doubled, the resistance will also be doubled. The new resistance will be 40 ohms. Now, over here, let's try this one. If I double the area, I take this piece of wire, all right, and let's say that this piece of wire is also 20 ohms. All right, if I double the area, see how this one is the same length, but twice the area of that one, right? What is the resistance of this piece of wire going to be? I doubled the area. Now look again. Resistance and area are on opposite sides of the equal sign. One is on top, one is on the bottom. This is an inverse relationship. So what that means is that if you double the area, the resistance will be halved. All right, so the new resistance of this one would be only 10 ohms. Now try it over here. Try it using the math trick, the shortcut. All right, nothing on the top has changed, so I'll put a 1 over there. The only thing that happened is that the area was doubled. That's going to be 1/2. All right, or you could say 0.5. The resistance of the new piece of wire with double the area, everything else the same, will be 10 ohms, or half of the resistance of the original piece of wire which we were comparing it to. Here's a more difficult problem. What if I triple the length and the area? What's going to happen to the resistance? Here I have a piece of wire, and the resistance of this piece of wire is 30 ohms. What if I triple 1, 2, 3 the length, and I also triple the area? The area is also 3 times bigger. Well, let's figure it out using the math shortcut. If I triple the length and triple the area, that's going to be 3 over 3. That's going to be 1. In other words, the resistance did not change. The resistance will remain the same. The resistance will remain the same. In other words, the resistance of this piece of wire with triple the length and triple the area is still 30 ohms. Another more difficult problem, right? What happens if I quadruple the length? Quadruple means multiply by 4, right? What if I quadruple the length and reduce the area to 1/4 of its original value? What's going to happen to the resistance? Well, here we have a piece of wire, right? Here's the length, here's the area, the cross-sectional area. If I quadruple the length, right? 1, 2, 3, 4. Right? This one is now 4 times the length that this one was. But I reduce the area. We make the area smaller. We make the area 1/4 of the original area. Okay, what's going to happen to the resistance? Now, the original resistance is 10 ohms. So here we go. All right, up here. If I multiply the length by 4, the length is now 4 times, and the area is 1/4 of what it was, then what we have is 4 divided by 1/4. All right, I can simplify this. I invert and multiply top and bottom. This cancels. 4 times 4 would be 16 times. All right, so the resistance would be 16 times what it originally was. The resistance, instead of 10, the resistance of this one would be 160 ohms. All right, 16 times 10. Now, there's another way you could look at this. You could say 4 divided by 1/4 is 4 divided by 0.25. On your calculator, plug in 4 divided by 0.25. You're going to get 16, just the same. All right? So one way or the other, the resistance new, right, the new resistance is going to be 160 ohms, or 16 times the original resistance. Last example. What if we halve the length, right? What if the length becomes half of what it was? Now, here's the original length. This one is half. And we reduce the area to 1/4. The area was big, now it's 1/4 of what it was. So we halve the length and reduce the area to 1/4. Let's figure out what would happen to the resistance. Now, the original resistance is 3.5 ohms for this piece of wire. All right, so we've got 1/2 divided by 1/4. You can invert and multiply. All right, 4 over 1. 4 over 1, that cancels. 4 divided by 2, right? 4 divided by 2 is 2 times. So the resistance will be double what it was originally. So instead of 3.5, the resistance of this wire is going to be 7 ohms. Now the other way that you could do this, all right, well, 1 divided by 2, 1/2, is 0.5. 1 divided by 4, 1/4, is 0.25. 0.5 divided by 0.25 is also going to give you 2 times. All right, so the new resistance is 2 times the original, 2 times 3.5, or 7 ohms. All right, 2 times the original value, or 7 ohms. Here's our first real wire equation problem. Calculate the resistance of a 5.0 meter long piece of silver wire with a cross-sectional area of 4.00 times 10 to the negative 7 meters squared. You want to first list your givens. We were given a length of 5 meters. We were given the fact that it is silver wire, so we immediately look up the resistivity of silver on the chart. We look up the resistivity of silver, we get 1.59 times 10 to the negative 8 ohm meters. Excuse me. They also gave you the area, and the area is 4.00 times 10 to the negative 7 meters squared. They're asking us to calculate the resistance. So there's your question. That's what you're trying to find. You're trying to find the resistance. You're going to put the answer here. It's going to be in ohms, and that's what we're trying to figure out, so we put a question mark. All right, so let's come up with a formula that has all or most of these quantities. So the formula would be R equals rho L over A. All right, the wire equation. R equals rho L over A. Okay, let's start plugging in. Rho, all right, the resistivity, 1.59 times 10 to the negative 8 ohm meters. The length, 5.0 meters. All right, and the cross-sectional area, all right, 4.00 times 10 to the negative 7 meters squared. All right, now you might see right off the bat here that the meters squared on top is going to cancel with the meters squared on the bottom, and you are going to end up with the correct unit for resistance, which is just ohms all by itself. So the units are working out just fine. All right, plug this in, 1.59 times 10 to the negative 8 times 5, hit equals. All right, now hit divided by 4, shift E, negative 7. All right, and the answer comes out to, all right, R equals 1.987 times 10 to the negative 1 ohms. Now, we only have 2 significant figures that we can actually hold on to in the answer. So 2 significant figures, the 8 bumps this up to a 2. So it's going to be R equals 2.0 times 10 to the negative 1 ohms. All right, and 10 to the negative 1 would just be R equals 0.20 ohms. That's a nice number. I like that number. All right. Now, let's look at some more possibilities here. All right, what if we were to double the length? If we were to double the length so that the new length, okay, let's just say, where do we want to put that? Tell you what, let's put that over here, okay? Now here, let's put the answer over here, all right? So there's your 0.2 ohms is your final answer, all right, with the correct unit. All right, now I'm going to erase a little bit over here because let's look at how we can use the relationships in this equation to figure out some other questions very simply. What if we were to double the length to 10? If we double the length, there's a direct relationship between length and resistance. The resistance is going to double. So, all right, if L2, let's say the new length, equals 10 meters, then R2, the new resistance, would be double this. The new resistance would be 0.40 meters. Okay? Now, what if we were to halve the length? Instead of 5, what if the length of the wire was 2.5? Remember, everything else stays the same. So let's just say if the new length, L3, all right, is 2.5 meters, or half, what's going to happen to this resistance? Right, it's going to be half also, because the relationship between length and resistance is direct. So that means that R3 would be 0.10 ohms. Can everybody see all of that? All right, now, what if we were to double the area? Instead of 4 times 10 to the negative 7, what if the area were changed to 8 times 10 to the negative 7? What if the area were double? All right, here, let's say if area 2, all right, if the new area, you know what, I tell you what, let's just use up here and erase this, because you can go back in the video and see anything that you need to see. R2, all right. Okay, so what if, all right, what if area 2, right, what if the new area were 8 times 10 to the negative 7 meters squared? Now, if you double the area and resistance are inversely related, so if you double the area, the resistance will be halved. The new resistance would be half. The new resistance would be 0.10 ohms. Right? And what if you were to halve the area? Instead of 4 times 10 to the negative 7, what if you halved, right, halved, what if you halved the area, not halved, halved. What if you halved the area to 2.00, right? If the new area were 2.00 times 10 to the negative 7, right? If this were half on the bottom, if this is halved, this will be doubled. So the new resistance would be double this. The new resistance would be 0.4 ohms. Okay? Now let me just show you quickly why halving the area doubles the resistance. Okay? Let's take a quick look at that. Because you might not see that right away. I didn't change anything on top, so I'm going to put a 1 up on top. All right? The bottom was halved. So what we're getting over here is 1 divided by 1/2. I'm going to reduce this. You can plug into your calculator 1 divided by 0.5, right? Or you could say invert and multiply top and bottom. So I invert that, multiply top and bottom, 2 over 1, right? That cancels. And on the top we get 2 times 1 equals double. All right, remember we said if you're going to halve the area, the resistance would be doubled. So when you halve the area from 4 to 2, you doubled the resistance from 0.2 to 0.4 ohms. Well, I hope you did problem number 2 on your own. You just follow what you did for problem number 1, and number 2 should be no problem. All right, here we are with problem number 3, a different type of problem. Calculate the resistance of a 0.75 meter long piece of gold wire. The radius of a cross-section of this wire is 9.775 times 10 to the negative 1 millimeters. All right, so you've been given the radius, the length, and the fact that this wire is gold. So you look up the resistivity of gold, and there you have it. They're asking you for the resistance. And you say to yourself, well, I have a feeling I'm supposed to be using the wire equation. In other words, R equals rho L over A. But the problem is we don't have the cross-sectional area of the wire. But we do have the radius of a cross-section of this wire. We have the radius. The cross-section of the wire is a circle, and the radius is this much. So you can figure out the area, the cross-sectional area, by using the equation for the area of a circle. Now your first step is going to be converting millimeters to meters. All right, so I tell you what, let's get rid of this for just a minute. All right, I'm sure we'll copy it again in a few minutes. All right, step 1. We're going to convert 9.775 times 10 to the negative 1 millimeters all right, to meters. We're going to use the factor label method, very similar to dimensional analysis. We have millimeters on top, right? This is all over 1. We want to put millimeters on the bottom. We want to get rid of the millimeters and convert them to meters. Here and here must be equal. 1 meter is equal to 1,000 millimeters. So now if we take 9.775 here, 9.775, second E negative 1, divide that by 1,000, all right, we're getting 9.775 times 10 to the negative 4. 9.775 times 10 to the negative 4 meters. All right, so now we have the radius in meters. Now we have the radius in meters. We can now calculate the area of the circle, which would be the cross-sectional area of the wire. The area of a circle, pi r squared. All right, so pi, we're going to put 3.14. R is right here. 9.775 times 10 to the negative 4 meters. That gets squared. All right, do all that math. All right, I've still got the 9.775 here. I'm going to square that, raise that to the second power, then multiply by 3.14, and we get, for the cross-sectional area, we get 3.00 times 10 to the negative 6. Yes, to the negative 6 meters squared. All right, so now you have your cross-sectional area. Okay, so now let's calculate the radius of, the resistance of the wire. Too many R's. Okay, here we go. I'm going to come down here. All right, so the resistance would be rho L divided by A. Rho for gold is 2.44 times 10 to the negative 8 ohm meters. The length is 0.750 meters, and the cross-sectional area right here, 3.00 times 10 to the negative 6 meters squared. Okay, let's see what we get here. Okay, 2.44 second E negative 8 times 0.75. I'm going to hit equals, and then I'm going to divide by 3 second E negative 6. All right, 6.1 times 10 to the negative 3 ohms. All right, 6.1 times 10 to the negative 3 ohms. All right, now, I mean, there's no reason to convert this to a decimal, but just for the record, that would be 0.0061, all right, ohms. Okay, so we have calculated the resistance of this piece of wire. All right, what you should do also is go to the website, either sciencehelpnow.com or new2.sciencehelpnow.com, download the worksheet that corresponds to this section, and do problem number 4, all right, and then we will go on to problem number 5. Remember, problem number 4 is similar to the problem we just finished, problem number 3. I'd like you to do number 4 on your own, using problem number 3 as a guide. Here's a slightly different type of problem. Problem number 5. A 30 meter piece of wire has a cross-sectional area of 5.18 times 10 to the negative 7 meters squared and a resistance of 3.243 ohms. Determine what metal or alloy, an alloy would be a mixture of 2 or more different metals melted together to make a solution. Determine what metal or alloy the wire is made of, limited to the materials, the choices, on the resistivities chart for the New York State Regents Physics reference tables. So we were given length, area, resistance. We're asked to figure out what type of metal it is, in other words, the name of the metal or alloy. So we're going to have to figure out the resistivity and then look up the metal on the chart by looking up its resistivity. All right, so what we need to do is calculate the resistivity. So here's our equation that matches all these givens and what we're trying to find. All right, R equals rho L over A. Now, if we're going to try to calculate the resistivity, we want to get the resistivity by itself. I put R over 1 and cross multiply. Right? R times A equals rho L. Right? And then to get rho by itself, divide both sides by L. And the equation we will be using, right, is rho equals R times A over L. All right, at this point, I'm going to erase that. All right, and just copy it over so we can start with that equation. All right, now remember, you have to know how to rearrange these things. All right, so we've got rho equals R times A over L. So the resistance we were given, 3.243 ohms. The cross-sectional area, 5.18 times 10 to the negative 7 meters squared. And the length was 30 meters. All right, so we do our math. All right, 3.243 times 5.18 times 10 to the negative 7 equals, okay, hit equals, now hit divided by 30 equals, all right, and we're getting rho equals 5.59 times 10 to the negative 8 ohm meters. All right, so I'm going to pull up the chart for you. All right, so take a few seconds and look at the chart and figure out what number on the chart corresponds to our answer here, we hope. All right, so take a look at the chart. There you go. So I'm sure you decided that rounding this up, all right, rounding this up to 5.60 times 10 to the negative 8 ohm meters, or at very least the best match on the chart would be, all right, tungsten. So this wire is made out of a pure metal, tungsten. Now I'd like to do a type of problem that seems very difficult at the beginning, because what you have, I'm going to call this a comparison problem, where you're comparing two setups. It might be a before and after where you have two different times. It might be two different situations. It might be two objects that you're comparing. Or it could be two different sets of conditions for the same one object. Maybe you're changing the temperature or the length of that object. Now, what you find with this type of a question is that some quantities are the same for the two setups, and other quantities are different for the two setups. And because of all this, excuse me, the problem seems very difficult. I want to show you how to make this type of problem really, really simple. So in a comparison problem, you have two situations. And part of the thing that makes it so difficult is that it seems like you've got way too many variables. Now, some of them also you don't know. So that seems like a huge problem. What you want to do, step one, would be to select an appropriate equation, and then put all of the factors that are equal for the two situations together on the left side. I'll demonstrate that in just a moment. Then step two would be, since you have the first situation and the second situation, you have A equals B, where A is all the factors that are equal, and A equals C, again, A is all the factors that are equal. Now, since A is obviously the same as A, that means you're going to be able to set B equal to C. Now, this is called the substitutive or transitive property of mathematics. I'm going to put up problem number 7, and we're going to use these two steps to make problem number 7 a snap. All right, so we have here a problem. A piece of aluminum wire, 10 meters long, has the same resistance and the same cross-sectional area as a piece of gold wire of what length? Now, you look at this problem, you've got two different objects, but there are some things about the two objects that are the same. The resistance of the two objects, the aluminum wire and the gold wire, is the same, and the cross-sectional area is the same. All right, so we know that R and A are supposed to be the same. Now they're asking us about length. The aluminum wire is 10 meters long. They want to know what's the length of the gold wire. So we know that L could be the same or probably different. All right. Now, we also have aluminum and gold, so we know we can look up the resistivity of each of those metals on the resistivities chart. All right, so these two are likely different. All right, so we've got quite a few. All right, we've got quite a few variables here, and we're like, ugh, you know. Well, we don't know the resistance, we don't know the area. All right, now, the first step on our list of possible steps a few moments ago was to select an equation. Now, I'm going with the wire equation because I see all the components of the wire equation here. We've got resistance, we've got cross-sectional area, length. We can look up the resistivity of aluminum and gold. All right, so this is the equation that I'm thinking is going to help me out. But of course, I've got a problem. I've got two unknowns. I don't know R and I don't know A. All right, so that's a problem. So let's go to that step one where we take all of the things that are the same about the aluminum wire and the gold wire and put them together on the left side. So it's the resistance and the cross-sectional area that are the same. So if I cross multiply, right, like that, and R is over 1 like that, I get R times A equals rho L. Everything that's the same about the two situations is together on the left side. I know it doesn't really matter if you put them together on the left or you put them together on the right. Just pick one. So I've put them together on the left side. Now we want to look at the aluminum and we want to look at the gold. We'll look at the aluminum over here. We'll look at the gold over here. All right, so I'll erase this. All right, and you can just keep writing. All right, I'm running out. You have lots of paper. I run out of space pretty quickly here. So for the aluminum, we've got Ra equals rho for the aluminum times L for the aluminum. Al is the symbol for aluminum. And then for the gold, we've got Ra equals rho for the gold. Gold is Au times the length of the gold, Au. And what we find is that if A equals B, all right, this is A, this is B, all right, and A equals C, all right, not the same A, by the way, all right, what we find is that B would obviously be equal to C. In other words, if this equals Ra and this equals Ra, then this equals this, B equals C. All right, so what I'm going to do is now set this part here, all right, rho aluminum, L aluminum equals, right, rho gold, L gold. All right, so what you've done is you've eliminated the stuff that was the same. The resistance and the cross-sectional areas were the same, and you've eliminated them. Well, you didn't know them anyway, all right? So that's what's great about this technique. All right, now we have an equation where we know 3 of the variables, and we're just trying to find the 4th. All right, the 3 that we know, all right, we look up the resistivity for aluminum. All right, the resistivity for aluminum is 2.82 times 10 to the negative 8 ohm meters. The length of the aluminum wire is 10 meters equals the resistivity for gold here, all right, is 2.44 times 10 to the negative 8 ohm meters. And what we don't know is the length of the gold. That's what we're trying to figure out right there, the length of the gold. So I'm going to multiply these two and then divide by this one. Multiply these two, divide by that, and we've got our answer. All right, so 2.82 second E, 2.82 second E, negative 8. I mean, obviously this is going to come out to 2 times 10 to the negative 7, but we'll do it anyway, times 10. All right, 2.82 times 10 to the negative 7 divided by this 2.44 second E negative 8 divides, so we're getting, okay, that came out wrong, hold on, 2.82 second E negative 8 times 10 equals, divided by 2.44 second E negative 8 equals, all right, 1.155 times 10 to the first. All right, the length of the gold, 1.155 times 10 to the first meters. All right, so that's 11.6, let's say. Do we have three significant figures? Okay, we've got three significant figures. All right, so our final answer, I'm going to put it up here. All right, the length of the gold wire, all right, is 11.6. All right, 11.6 meters. Okay, now obviously here also we should have just canceled the 10 to the negative 8s before we started doing the math. That would make the math quicker and easier. Okay? And so this is a great way to take a problem that looks incredibly difficult and make it much simpler. Remember, the first step, when there's two different situations that you're comparing, and they have some things in common, is to take the equation that you feel is going to get you to that answer. You know, that a lot of the stuff that was mentioned up here, your givens, lets you know what equation you should probably start with, and get all of the factors that are the same for the two situations together on the same side. Now, just one quick little check if our 11.6 meter answer makes basic sense. All right, we're just going to look at whether there's a direct or an inverse relationship when we change the resistivity, right, between resistivity and length. Is there a direct or an inverse relationship? Now, we know that we want the resistance in the cross-sectional area to stay the same, so we're not going to touch either of those. We know that the resistivity for aluminum, all right, is 2.82 times 10 to the negative 8th ohm meters. We know that the resistivity for gold, all right, is 2.44 times 10 to the negative 8 ohm meters. So when you change from aluminum wire to gold wire, the resistivity decreases. Now you can see that there is an inverse relationship between resistivity and length. Since there is an inverse relationship, we expect that the lower resistivity would mean, in order for this to stay the same, for the resistance and the cross-sectional area to stay the same, if the resistivity decreases, the length of the wire would have to increase, which it did. It went from 10 meters to 11.6 meters. All right, so it makes sense that the length of the gold wire would be a little bit longer than the aluminum wire. So we've done like a nice little check on all that math that we did.